Alright, welcome back to another video of my channel, math_exe. Today I'm going to look at a element of introductory proof, or just like if you want to prove a mathematical statement in general, which is proof by induction. So I would just title this video the Art of Induction because I think this method of proof is one of the most beautiful ones among all. So let's just jump into it. So suppose you want to prove a statement P of n of all natural numbers n. So let's just write that in. So first we're going to write the base case. And for the base case, we can just substitute n equals 1. And then after that, it's pretty simple. We can just substitute n equals 1, and then from that you need to show this is true. And if you're done with the base case, now is the tricky part, which is the induction hypothesis. And then we need to show that for all k in natural numbers, it satisfies this property. So we have p of k implies p of k plus 1. And what that basically means is if p of k is true, just note that with a check mark, that also implies that the next natural number input will also be true. So this is a pretty powerful property because if you somehow have arrived at this property by either writing out the pk plus 1 case and then substituting p of k into that, and then kind of just work things out. And this is why it is pretty difficult, because there are like infinitely many strategies to find this property of the induction hypothesis. Anyways, after you've done these two steps, you're pretty much done, because notice that we've shown that p of 1 is true. And using our property from the induction hypothesis, if a natural number input is true, then the next natural number input will be also true. So that implies p of 2 will be true. And then doing the property yet again, we have p of 3 will be also true. And then doing it again, and then doing it again, and then so on, leaving with a chain reaction that implies all natural numbers to be true, all natural number inputs to be true. Alright, so that's just like the basic concept, like the structure of this proof, of the strategy of proof. So I'll just jump into an example involving this induction. Alright, so here's an example. We need to prove that the sum of the first n odd numbers, which is just 1 plus 3 plus 5 plus all the way to 2n minus 1, is n squared. So this is a pretty easy example that I want to show you. So let's just jump into it. So part 1 is the base case. And this is typically easy to see, because when you substitute n equals 1, we get that the sum of the first one odd numbers, which is just 1, is equal to 1 squared. And this is obviously true. So no denying about that. And the next part is the induction hypothesis. And then we need to suppose that for all natural numbers k, it satisfies that p of k implies p of k plus 1, which means if p of k is true, then p of k plus 1 is true. So what I would like to do is I'm just going to write the k plus 1 case, which is just 1 plus 3 plus 5, which is the sum of the first k plus 1 odd numbers. And I'm just going to write this very carefully. So this is the kth odd number, and then we have our k plus 1 odd number right here. And then expanding this inside this bracket, you'll get this is equal to 2k plus 1. And we must show that this must be equal to k plus 1 squared using our case up here. Alright, so the reason I've written it like this is because notice these first terms right here, and notice this is just equal to k squared. And you can just quickly notice that using the formula. So this quickly simplifies into k squared plus 2k plus 1 is k plus 1 squared. And notice k squared plus 2k plus 1 factors as a perfect square, which is just k plus 1 squared. And we're done with this part. And then for the whole proof, we're just pretty much done at this point. So you can just put a QED or box right here. And it's because that we have shown that our first case is true. So we have P of 1 is true. And then using our property that we have shown that if a natural number input of the statement is true, then the next natural number input of the statement will be also true. So using that property and then doing that property again for k equals 2, you get a chain reaction that makes all natural numbers satisfy this case. So yeah, that's all I have to say for this video. So hopefully you guys enjoy this video. Please subscribe for more, and I'll see you guys in the next one.